Okay, this is, to give a little bit of background, this is work that I did in collaboration with Gabriela Berenboim and Juan L. Park at University of Valencia. And also that itself built on some work that I did with Katie Fries a couple of years earlier, talking about conditions for eternal inflation. And the basic summary here is I walked into this trying to get rid of eternal inflation, instead found that it was a lot harder to do than I expected. So if you don't like eternal inflation, you're kind of screwed here is the basic message. And there's nothing, I'm not going to say anything terribly deep or profound. A lot of this is stuff that's known. I will consider this talk successful if half of the audience thinks it's trivial and obvious and the other half thinks it's completely wrong. And I will consider it extra successful if anybody is convinced of both. So let's look at a simple system of single field inflation, and I'm just going to do simple, basic, canonical single field inflation, although a lot of these arguments would probably apply to non-canonical models as well. So I have a field rolling down a potential, 1 degree of freedom, and the correct way to handle these kind of systems, including quantum back reaction of fluctuations from the field, is to write down a Fokker-Planck equation. So you have the usual classical equation of motion for the scalar field, and then you include quantum effects by adding a stochastic driving term on the right-hand side. I'm not going to do that, because that's complicated. What instead I'm going to do is come up with sort of a set of basic simple order of magnitude arguments for when you expect eternal inflation to happen, when it doesn't, and ultimately I want to relate this to arguments about effective field theory and a couple of other things that you might find interesting. So the basic concept, the basic idea here is you have two kinds of evolution, right? You have classical evolution, and you also have quantum evolution happen. So the field is going to be jittering around, and we all know that the eternal inflation basically happens when the quantum fluctuations dominate over the classical evolution. And that's the condition that I'm going to use here. So in particular, I have that the field evolution, classical field evolution in a Hubble time, is just phi dot divided by the time divided by the Hubble parameter during inflation. Right? So that's how far the field rolls in one Hubble time of expansion during inflation. And similarly, I have a quantum fluctuation amplitude, which I'm going to define to be the root mean square expectation value of the field fluctuation on scales of order the horizon size, which is the familiar h over 2 pi, right? We all know this. And so the condition for eternal inflation then, that we're going to use, and there's nothing new about this, but writing it in this way is a little bit unusual, is that I want this ratio has to be bigger than 1, okay? And we all recognize what this expression is. This is just the scalar curvature perturbation. So a simple back-of-the-envelope, necessary but not sufficient condition for eternal inflation is just that you have a co-moving curvature perturbation that is non-perturbative, that's greater than the unity. And this, of course, is where it's going to feed into arguments about effective field theory and inflation. Right? So this is going to be our basic condition for eternal inflation, is when the field rolls far enough up the potential that quantum fluctuations dominate, that condition is exactly identical to the co-moving curvature perturbation being greater than the unity. Okay? Pretty simple. So let's take a look at the very simplest case we can come up with. How am I doing? Oh, not very well. All right, good. In particular, power law behavior. And I'm just going to summarize the results here. These papers have the details of how these calculations go. They're not very complicated. If I have an exact power law where is related to the slow roll parameter epsilon in that way, where epsilon is a constant, then it's pretty straightforward to work out that CMB normalization, right? I can't draw that up any further. Implies that on observable scales, so the Hubble parameter when CMB fluctuations were laid down ends up being about 6 times 10 to the minus 5, and this is just equal to 2 pi and I think that should be a 1 minus n, shouldn't it? Yeah. So if I assume that it's a pure power law, right? Epsilon is constant all the way through, I can normalize it in this way, and I find that eternal inflation, so at what wave number does the curvature perturbation grow to greater than unity? So as I go further and further up the curvature perturbation is getting bigger because it's a red spectrum, right? So I find that if I work this out, the difference in wave number between eternal inflation and the CMB is about a factor of 10 to the minus 217, which is a ridiculous and absurd extrapolation. No one would believe extending this pure power law that far. But if you take this at face value and you look at this, you can use an important relation, which is K over H, dH by dk is equal to epsilon over epsilon minus 1. And this is important because this is an exact relation. It doesn't depend on slow roll, it only depends on single field inflation. This tells you that H eternal inflation over H star is of order, is around 2 times 10 to the minus 4, or H eternal inflation over, in units of the Planck mass, is about 1.28. What that tells you is that if I assume pure power law behavior, eternal inflation never happens. I have to have a Hubble parameter that's bigger than the Planck mass in order to do it. So, lesson 1 here is that eternal inflation requires epsilon to get small as k gets small. Now I'm just going to write that as epsilon goes to 0. It just has to be a whole lot smaller than it is constrained with the CMB, right? Because CMB tells me that n minus 1 here is about minus 0.04. That fixes epsilon. That means that h has to grow too quickly in order to accomplish eternal inflation. This is just an observational limit. So how do I get this kind of behavior? There are basically 2 ways to do it. So case 1 is something like a chaotic potential, right? So if this is m squared phi squared, this kind of a potential has the neat property that phi dot in slow roll is actually a constant everywhere on the potential. As long as the slow roll approximation is good, my field velocity is a constant. And but as I grow further and further up the potential, my Hubble parameter grows, and so I have that H eternal inflation is much, much greater than H star, but it's still subplanckian in this case. You can work out the numbers. This is a familiar case of eternal inflation. In fact, what I find here is that because essentially the epsilon goes like m Planck over phi squared. As I go up the potential, epsilon goes to 0 and I enter a quasi-de Sitter phase of expansion, and everything works out. H grows slowly enough that I can have greater than unity curvature perturbation, but a subplanckian Hubble parameter. The second case, and this is the more interesting one, I think, because this is ruled out by data, right? the Planck constraints favor low-scale inflation, some sort of small field, generally either a hilltop or a plateau-type potential, is, and here's the case, here's the simple case I'm going to look at. So I'm going to mock up a hilltop potential as being a top hat. So this is the toy model I'm going to look at, where I have v of phi is equal to some non-zero v naught, as long as the field is less than some width delta, and 0 otherwise. And this is going to be a toy model, and I'm going to argue that this applies to more realistic models like Higgs potentials and whatnot, okay? So how am I doing on time? Another 10 minutes? 10-ish. Okay, so under what conditions, so what does the field evolution look like here? Well, in particular, this is a really crazy potential, because in fact, the slow roll solution, so I'll start over here. I'll leave my title slide up. I guess I should be erasing these long enough ahead of time for them to dry out. Okay, so I'll let that dry for a second. In slow roll, I have, right? I just have that finite vanishes, right? The classical field evolution here is that this is just a plateau potential. The field doesn't move at all. And so this is an extreme case of eternal inflation in which that the P of K is actually divergent. This expression here goes to infinity. All right, so we definitely trivially apply satisfy the case of the condition for eternal inflation, is that all the field evolution here is quantum mechanical, none of it is classical. And this thing is going to random walk around here until it eventually falls off the edge of the potential and we reheat. So this is my inflation model. Okay? So this is the case of what's called ultra-slow roll inflation. That is inflation on a completely flat potential, where the classical solution is phi dot is equal to 0. And you can work out, for example, the curvature perturbation in this. And in the case where you give it a small non-zero field velocity, the curvature perturbation actually ends up, the perturbation spectrum ends up being very large, but scale invariant. So what you get out of this is a scale invariant spectrum. However, you notice that in the limit that phi dot goes to 0, something funny happens, which is something funny happens to co-moving gauge. So if I look at the Mukhanov variable, I have that. So this is my canonically quantized variable corresponding to the co-moving curvature perturbation, is defined to be A delta phi minus A phi dot over H zeta, where this is that's my co-moving curvature perturbation there. And you can see exactly what happens. In the limit that phi dot goes to 0, I can't consistently take co-moving gauge, which is setting delta phi is equal to 0. So the curvature perturbation spectrum, of course, doesn't diverge. The only thing that diverges is the co-moving curvature perturbation, not because there's anything unphysical happening, but because co-moving gauge is singular. I can't take co-moving gauge because phi dot is equal to 0, and so this term goes away. And so the only self-consistent gauge I can take for my perturbation amplitude, my canonically quantized perturbation variable, is flat gauge. And you can do the calculation in flat gauge and you get a scale invariant spectrum of curvature perturbations at the end of the day. So here comes my argument about effective field theory, is this is a really nice case where in fact doing an effective expansion of the inflationary dynamics in zeta fails utterly because the gauge in which you're doing the expansion doesn't even exist in this case. So you can now work out, in fact, that, how many minutes? 5 minutes, all right. So the condition for eternal inflation here now is a little bit different because the co-moving curvature perturbation is infinite everywhere, so I can't really use that condition very, very usefully. But what I can say is I can assume I have a random walk here with a lifetime that looks like, so the average time, the average lifetime of this quantum state is given by H inverse delta over the quantum squared. Right? So if you do a random walk and say this field is just random walking along there, the number of steps you take in the Hubble time is h times this lifetime, so that you end up with an average lifetime for the field like that. And so I can say that the decay time for an inflationary stage is approximately t over this lifetime, right? But meanwhile, the volume of an inflating phase goes as a cubed is proportional to e to the h 3ht, right? So if I take an inflating patch, that thing in time t, the volume of that is going to increase by a factor of e to the 3ht. So that means I have eternal inflation if 3 minus delta phi q over delta squared ht is growing, right? As long as that factor in the, as long as those time constants are positive rather than negative, then the expansion is going to win over the decay of the false vacuum state, and I have eternal inflation, which can then be worked out to a condition that delta in units of the quantum fluctuation amplitude has to be greater than 1 over the square root of 3. And more importantly, if I put this in terms of the scales of the potential, the height and the width of the potential, I end up with the following relation. And this is the second important conclusion of this talk, is in particular that if I take this V naught is some scale that I'll call lambda to the fourth, this condition, when I plug in the correct numbers, ends up being that the height of the potential divided by the width of the potential, and I should probably use something other than lambdas and deltas, but you can read that, I think, is greater than the height of the potential over in Planck units. And here's the important thing, is that there's no Planck scale in there, right? It just is the ratio of the height of the width of the potential has to be greater than the height of the potential in Planck units, which means that I can drop the energy scale of inflation as low as I like, and I still will have this property of eternality, right? There is no, decoupling doesn't happen here. No matter how low my energy scale is, I can still always have eternal inflation. And in fact, you can show that this also holds in more realistic potentials where you have something like this, okay? And that's in the original references, but basically it's for exactly this reason that it only depends on the ratio of the height of the width of the potential and doesn't depend at all on the absolute scale of the thing. So this represents what Eva Silverstein calls dangerous irrelevance. As in, essentially, a failure of decoupling. I have large gravitational effects at arbitrarily low energy scale. The gravitational back reaction is big. No matter how low I go, I could have inflation at a TeV, and I would still have these very large gravitational back reaction effects, and there's no suppression by the Planck scale. So here's my attack on effective field theory, is number one, effective field expansions in zeta don't work at all because zeta is not even defined because the gauge is singular. And second, this is dangerously irrelevant in the sense that there is no suppression of these large corrections from gravitational effects that are suppressed by some higher mass scale. In fact, they happen at any energy scale whatsoever. And so in this case, you're never going to be able to use effective field theory to understand the physics here. So, am I out of time?
Yep.
Perfect. Thanks.